Visible?
Yes, sir.
Yes, yes, sir.
Yes, sir.
Visible from this line, right? Or even bigger? Can you see this one?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes.
Here also. Here also.
Yes, sir.
Okay. I'm going to expand the board a little bit. I have to write a big matrix. Okay. Just let me know if it is not visible. Okay, so far what we are doing. So we just introduced to point groups, symmetry elements, and then we also saw what is called as groups. After groups, we started working on a matrix representation, right? Matrix representation. We just started, and I was telling there are two type of way of representing it. The symmetry operations in the matrix itself. One is either by Cartesian coordinates you can represent, or by position of atoms. If the position of atom change, you can also write in terms of a matrix. So last class we saw about the Cartesian coordinates. There is a rotation, plane, how the matrix can be written. I will start with the same molecule, the ammonia molecule, then write the matrix form when we move the atoms. Okay, so how the matrix will represent? I mean, how the matrix will look like, we just see. So again, we just start with C3V matrix representation. This is for when atoms are moving. Okay, so C3V, we just take an example, ammonia itself. So I write, let me draw. So basically, I'm writing ammonia in a different way. Okay, so last class somebody was asking water molecule. Why not you consider the lone pair electrons also? Like here in all these group theory, we don't consider the lone pair electrons to define the point groups. So water is considered as just, of course, there's a distorted tetrahedral. In water, there are two lone pair of electrons, right? On the oxygen atom, we don't consider that. In ammonia also, there's one lone pair of electrons. We don't, because there's no bonding here. We don't consider that. Okay, so we just simply see the atoms, how they are connected. So that's why it is water is C2V. It's a planar molecule. Ammonia is non-planar, C3V. Okay, so that's why we are considering water as just planar. So I just write ammonia in this fashion. Just nitrogen atom in the center and three atoms H at various corners. Okay, with this in mind, we can write E as, so there is no change of atoms. So I just write for E. Like this, there's no change for this. Let's do it for C3. When I rotate C3, no. So if you rotate it, so I can write HA, HB, and HC. I just call it as HA, HB, HC. If you rotate it, HA will come to here, HB will go here, and HC will come here. So there is a position change of this H. So for that, so if you consider first row as HA, so that changes to goes to the second place, whereas HB, which was originally here, will come here. And then one HC, which was here by rotation of C3, it will come here. It was earlier here, it will come here. So this is just the interchange of atoms. So we can simply write the matrix in this form. So this is for C3, and then C32, we can write as from starting, say this is the starting one. So for C32, two places it will shift. So C32, if you do, HA will come to this place, HB will come to this place, and HC will come to this place. So HA is 0, 0, 1, then this come to 0, 0, 0, and 0, 1, 0. So C32 can be written as like this. Okay. Now sigma plane. So let's try.
Sir. Sir. Sir, can you explain this once more?
Huh?
Sir, can you explain this once more, sir? C3.
Okay. C3, yeah. So as I was saying, these are various matrix representation. No, you can represent by various ways. One way is moving the Cartesian coordinates. That's what we did last class. Like you rotate the Cartesian coordinates where the x-axis is, if you rotate by C3 or x will become minus x if you place a mirror of sigma b plane, or z will remain such. So that is one way of representing. So that is that's why you saw negative signs in that matrices. Here in this case, what we are doing is we are rotating the atoms in the molecule, okay, by these operations. So that we are writing in terms of a matrix. So E is a symmetry operation, right? So we don't do anything. So atoms are located other places. Like it's not, there is no change. So this is a starting symmetry. We are not changing anything, so it just remains as such. It is HA atom, HB atom, HC atom. When you rotate C3, so HA atom goes to the HB position. Yeah, and HB will go to HC position. HC will come to HA position. So there is a 120-degree rotation, right? So this is what we are considering. This is X shifted to next atom position. Similarly, Y, HB, I mean the HB atom shifted to the next place when you do C3. And one which is the third position, the HC atom, when you rotate by C3, it comes to the HA position. So you can see these are on HA position, it just comes to this row from here to here. HA goes to the HB position. This is HB, right? So the first atom goes to the HB. So like that, we are writing the matrix. The shifting of atoms, we are writing in terms of a matrix form. Okay, I'll give more examples and you will appreciate better. C32 is 240-degree rotation, right? That means 2 times the atoms are shifting its position from HA to HB. HA goes from here to HC. So it has to go from, starting from here, it jumps to the HC position. HB atom jumps from here, originally it goes to 2 times, right? First time here and then second time comes here. HC is, it was originally here, then 2 times you have to jump, so first time and second time. So just if you rotate it, you get matrix for C32, something like this. Okay.
So here we are.
Sigma B also, then you will appreciate it better. Okay, just hold on for 1 or 2 minutes. Sigma B prime will just take, then you'll appreciate better. So let's fix the axis. Okay, so sigma B prime is, we are going to use this one. Sigma B double prime is cutting. So you know, sigma B prime is cutting through this atoms, right? In ammonia, we generally place mirror this way, right? So we are writing sigma B prime, and this is okay. So sigma B prime, if you place a mirror, what happens? So I'll place a mirror here. HA position is not going to change; it will remain as such. Whereas HB and HC will be interchanging. HB will go here, HC will come here. So sigma B prime, I can write the matrix as The HA is not going to change. So original place is 1. So I'm writing 1 there. 0, 0. Whereas HB has been shifted to the next place. So this will go here. And whereas this one will come here. So what happened was HA remains same, whereas HB goes to HC, whereas HC comes to HB. There's interchange of HB to HC and HC to HB, whereas HA remains as HA only. We can write HA. Okay, so the atom HA remains as HA, that's why it is 1, whereas HB goes to the HC position. So from here it has gone to the HC position, and HC has come to HB position. So from here it has jumped to this position. So this is for HA. Now sigma V plane, sigma V double plane. So sigma V double prime. So in this case, what do we get? Sigma V double prime. So I'm going to apply a plane through this and through nitrogen and HB. So if I do that, so if you place mirror something like this, only HB and HA and HC going to interchange. So I can write it here. HB remains as HB, whereas HA will become HC, and vice versa. HC will become HA. So HB is going to remain as HB. Okay. Whereas H1 going to jump to the third place. You'll get something like this. So HA portion jump to the C to HC, whereas HC has become HA, and HB remain as same. Now I'll write it for the third plane, which is passing through nitrogen and HC atom. So if I do that, so this is sigma V triple prime. Okay, so again this is much simpler. So what? HC is not going to change anything. So I write as 1, whereas HA will be interchanged with HB. So 0, 1, 0, and then B will come to A, 1, 0, 0. Okay, I can check it if it is correct with my notes. Yes, sigma V double prime is fine. Sigma should be fine, I think. Yes, 1, 0, 0. Doesn't matter. It's fine. Yeah, should be fine, I think. Yes, yeah. So you'll get something like this. So you have 3 matrices: sigma V prime, sigma V double prime, sigma V triple prime. Now, the group properties or group multiplication table, which you have worked earlier, right? By rotating the atoms or molecules, also valid with these representation. You can check. Say if you want to take the product of C3 and sigma V triple prime, you should get sigma V prime. So group properties like, or any example you take, sigma V prime with C3. Okay, you should get what? You should get corresponding matrix of its result. So sigma V prime is what we have written: 1, 0, 0, 0, 0, 1, 0, 1, 0. So this is sigma V prime. C3 is 0, 1, 0, 0, 0, 1, 1, 0, 0. So take the product, the matrix, 1 into 0, 0, 0, this into this. Okay, this into this, 1 you get. And 0. Okay, now you multiply this with this. So this will get 1. Again, it's going to be 0. This into this, 0, this into this 0, this into this. So 0, 0, 1. So if you take the product of sigma v prime and C3, so you get matrix of 0, 1, 0, 1, 0, 0, 0, 0, 1. So that is sigma v triple prime. So I can write sigma v triple prime. So you check it with your multiplication table. C3 multiplied by sigma v prime. Sigma v prime is sigma v triple prime. Correct or not?
Hello, sir.
Yes?
Sir, here we consider ammonia as a planar molecule.
No, not planar. That's why I put it in a square box.
But this is in a back face of the cuboid only, no?
Yeah, so basically it is occupying 3 positions. Ammonia is not planar.
Okay.
So nitrogen center, and then it occupies 3 positions. So one is you can say this is the bottom of it. Other one front side. So other one is here. So we can say this is outside the plate. So it is in a box. We have the atoms are occupying at 3 different locations. The hydrogen atoms are occupying at 3 different edges. So if it is a planar, means you have to keep hydrogen here, right? So this box is coming out. So we are not kept it here. We have to kept it behind. That's the reason. Okay. So the multiplication should be valid. What representation you take? Here in this case, we have taken changing the position of atoms. Yeah, and once you write the matrix for the each symmetry operation, and then if you take the product either way, it should result in the matrix multiplication table, which you have got it. Okay.
Sir.
Yeah.
If we have BCl3 molecule which is planar, so how can C3 and sigma V's are changing?
BCl3.
Yes, sir.
Okay. Yeah. So what is the problem? We can work out for BCl3 also.
I mean these matrices are same for sigma BCl3 and NH3.
You know, whenever you speak now, it's a voice problem. I'm not able to understand.
I mean, for BCl3 and ammonia, are these matrices are same or they will be different?
No, it cannot be. I think it will be different.
Because these also are rotating at 120 degrees and having C3s all, sigma V's all. That we have done for ammonia.
But BCl3 will have C2s.
So it cannot be C3V, right? What is the point group of BCl3? It is
D3H.
D3H.
D3H. So you will have different symmetry elements in that. So you cannot. There will be multiple matrices. Whereas in C3V ammonia, you will have only 6 matrices. Yeah. So 3 for sigma planes, 2 for C3 planes, and 1 is identity element. So D3H will have different number of matrices. So you can write the same fashion. I mean, something may be same, like C3 may be same. Okay, for C3, yeah, if you consider these are the axes.
Yes, C3s and sigma V's are same actually, but they also have C2s.
C2 is also there, yes. C3 may be same, but yeah, so C3, C2, all these things, this C3 is for ammonia molecule. The matrix representation of C3 is for the ammonia molecule or C3V point group. Okay, so it will be different for different molecules. Okay, so we are considering the atom position, so it could be different, or you'll have In BCL, DC, D3H, you will have C2 also, right? So that will be different. Okay, so for every molecule, you will have different matrices. It's based on the point group of the molecule. I hope.
Yes,
I hope it is clear. Huh? So
yes, sir.
work it out. You find out our matrix elements for matrix form of matrix representation of BCL3. Of BCL3. You find out it could be so since you are showing D3H, no, it's point group. How many elements are there? So many matrices are there. You just find it out. Considering this as this is a planar molecule, so it's much easier. You can find it out. There, when it comes to C2, so C2 is passing through this bond, right? You rotate it. So this atom will remain same, whereas this two will be interchanging. So interchanging means you just change the position, and then you can write it. So you can write it. Okay, just try it for BCL3. So what I'm saying is either you can move the axis or atoms you can rotate it. Based on that, you can write the matrices. The applications will come shortly while we are writing these things. We'll study what is called as block diagonalization in matrices. We block diagonalize the matrix. After that, we write in terms of a representation or reducible representation. And then we use what is called as a similarity transformation. By doing similarity transformation, we convert these matrices into block diagonal matrices where the elements will be only along the diagonal elements. Okay, now it's all scattered, right? So it's a 3 by 3 matrix. Elements are all present in lower left, top right. Here you can see there's a top right. So this is all reducible representations. So we use some technique to bring it to the irreducible representation. When you do that, convert from reducible representation to irreducible representation, all these elements will fall in the diagonal elements. Once we have in the diagonal elements, we simply sum it up. We find the rank of the matrix, and then say what is the dimension of the matrix. So if it is just only 1 by 1 matrix, we say it's a dimension is 1 dimension. If it is 2 by 2 matrix, it's a 2-dimensional matrix or 2-dimensional projection. If it is 3 by 3, then we say it's a 3-dimensional IRs. So we introduce these terms shortly, and these IRs, irreducible representation, tells about our vibrations. Whether it is vibrating in only one direction or it is along with x and y axis, I mean 2-dimension vibrating. So those things will connect it. For that, we learn what is called as a class. We use the word called as class. And we'll slowly go to that stage. So class is okay. Definition is it's a complete set of elements which are conjugate to each other. So before I go to the definition, I just write what is conjugate. So 3 terms we are introducing: class, similar transformation, and conjugate. So let's start with say you have a X inverse E X. So A and say these are the elements of elements present in the group. Okay, so A is an element, B is an element, X is another element, and X inverse is also another element. So if you have so many elements, if you perform this X, A, and X inverse, and if it results in B, then what we say is B is the similar transformation of A with respect to X. Okay, so what we write is so ABC or ABX are elements. So B is similar transformation of A with respect to X. Okay, so if we perform this operation, then we get this one, then we call it as a B is a similar transformation of A with respect to X, and A and B are called as or conjugate elements. So A and B is said to be conjugate elements. In a group, all these things should be valid. If you have three elements in a group, then if you write in this form A, then you multiply with X towards the right and multiply with X minus towards left. Then it results in another element B. So then A and B are said to be complex, A and B are said to be complex conjugate. And if you perform this, we get B, right? So B is called a similar transformation of A with respect to X. So this is one property. We can find out for C3 itself. We can find out what is the similar transformation. Okay, so I'll introduce class shortly, but yes, so this is. You agree with this definition? You agree? I mean, I'm going to give you an example. Okay, I'm erasing these wordings. So similar transformation of CP with respect to sigma B. Which one we take? Sigma B triple prime. Say you are asked to find out similar transformation of C3 with respect to sigma B triple prime. So what I do is so basically with respect to so question is what is the similar transformation of C3 with respect to sigma B? So this you have to find out. So you just sigma V triple prime inverse operator is C3 and then sigma V triple prime. So this operation you have to find out, and what is the answer? You just have to find out sigma V triple prime inverse multiplied by C3 and sigma V triple prime. So if you know the matrix representation of these things, it's easy to multiply and get the answer. Yeah.
Sir, C31 or C32?
C31 here. If I'm not writing anything, it's called C31. Okay.
Okay, sir.
So as you know, sigma V triple prime inverse is nothing but sigma V triple prime. Okay. So with this in mind, you can write sigma V triple prime C3 sigma V triple prime. So what will be the answer? Can you multiply first these two? So basically we go from the right to left. So you multiply these two. C3 into sigma V triple prime is what? One way you can use a matrix. If you are not aware of matrix, then you can simply write C. So this is z-axis, sigma v triple prime. So sigma v triple prime, we do that. Represent C, let's see, and then you write C3. So I'm performing by molecule. I don't have matrix now, so I'm just writing by the geometry itself. So I place a mirror on HC plane, HCN plane, and then only these two will be interchanged. That's what I've done it. And then C3 you have to multiply. So C3 you have to perform. So this C3 to perform. You rotate this one. The HB comes here, HA comes here, HC goes here. So we are rotating by 120 degrees. So if you rotate it clockwise, 120 C3. So just goes to other side, and I've done this, right? So two things I have done it. Now again I perform C sigma v triple prime. So sigma v triple prime is from this side. Place it. Nitrogen. HA. HC. HV. So I got this as a final structure. This is the starting one, HA, HB, HC. Now it has come down to HB, HC, HA. So we are performing. So how do we get that? So we can see the uniform HB, HA, HC. So this is coming because of 2. Yeah, from the starting to the end, if you can come by C32. So you rotate by 240 degrees. C32 to perform. HA will come, HC will come to this place. HB goes to this place, and then HA comes to this place. That's what it does now. So this answer is equal to C is called as C3 2. Okay. So the question is the similar transformation of C3 with respect to sigma v triple prime is C3 2. Okay. So this is one way, and then if you perform more, like you can do. You can try with C3 2 also, or sigma v here you can take, and then take C3 in both the sides, and then find out the similarity transformation. And we can find out what is the similar transformation of each element with another element. And if you do that, what you will get is rotation C3 will always result in, either C3 or C32 if you take. If you perform similar transformation with any of the element, it will result in always C3 only or C32 only. And similarly, if you perform the plane sigma v prime, double prime, triple prime, if you perform the similar transformation with respect to either of any of the elements, it will always result in sigma plane only. So it won't change. So what I'm saying is take C3 with E inverse. Okay, C3 with you can do itself. C3 inverse C3 with sigma v or C3 2. C3 minus 2. C3 sigma v prime inverse. C3 sigma v double prime inverse. C3 with sigma v triple prime inverse. If you do that, you can make it up. This is C3. This is what do we get? C3 into C3, C3 2, and then C3 2 into minus 1. So it again will be C3. So if perform this C3 2 into C3, it's E. So this is C3 minus 2, which is nothing but C3, I think, right? And sigma V prime into C3. This is important. This you can find it out. So sigma V prime into C3 is what? Sigma V triple prime. C3 2. So I'm doing first two, so that's what sigma V triple prime, and if only with another plane, sigma V prime, then this is the C3 2. So yeah, C3 into sigma V double prime, C3 into sigma V double prime. What sigma V triple prime will get? Double prime. Check now, ये तो check कर लो. I'm not getting correctly. C3 into sigma V double prime into C3. This is single prime. Okay, and then sigma V prime into sigma V double prime. C3 2. Again, if you perform this, again you will get C3 or C3 2 only. Sigma V triple prime multiplied by C3. Sigma V double prime. Double prime and triple prime. C3 2. So yeah, you can see if you take the C3 and find the similar transformation with respect to, I mean, if you perform with respect to E or C3 or C3 2 sigma V planes, you always end up with C3 or C3 2. So if you do that, then C3 or C3 2 form a class. Okay, so C3 and C3 2 form a class for, in C3.2 you have E C3 C3 2 sigma V double prime, V triple prime, right? So these two form a class, because if you perform the similar transformation with any of the element present in this group, will always result either C3 or C3 2. So that's what we are seeing. Whatever you do, you will end up with only rotational symmetry only. Now, if you perform with this one, you find out the similar transformation of sigma V plane with all the elements. If you perform, find out, say instead of this, I interchange with one plane. Okay. Say I just take it with sigma V prime. Okay, so if you perform this, yeah, so I'm taking sigma V plane prime and then finding out its similarity transformation. So what you will get? What is its conjugate element? So this one will be sigma V prime only. This one, C3 into sigma V prime. C3 into sigma V prime is sigma V double prime multiplied by C3 inverse. So C3 inverse is C2. So C3 double prime multiplied by C3 2 is sigma V triple prime. So you get only sigma V planes, I think. Okay, I hope it is visible. So if you perform this, C3 2 into sigma V prime. C3 into sigma V prime is sigma V triple prime. And then C3 minus 2. So C3 minus 2 is what? C3, right? So this is C3 into triple prime, sigma V triple prime multiplied by C3 is sigma V double prime. Similarly, one can go ahead and find out it's this one sigma V into sigma V is same, so all this is EA. Sigma, it's all sigma V. Fine. सिग्मा V into सिग्मा V कितना क्या होता है? E. And then sigma double prime multiplied by sigma prime. C3 sigma V prime. Let me finish this one. So C3 prime interval by sigma V prime. So the C3 2. So this will be C3 into sigma V prime, triple prime. Sigma V prime. Okay, you can see if you take one symmetry element, sigma plane, and find out its similarity transformation, you always end up with planes only, not the rotational axis. So plane of symmetry you always get. So these three, if you can repeat it with sigma double prime also, triple prime also, you'll find the same. So this one will form a class, and these two will form an underclass. Okay, so that's what I'm saying. So class is, now I'll come to the definition of class. Class is a complete set of elements which are conjugate to one another. So class is a complete set of conjugate. To one another or each other. To one another. So I give you, okay, so this is the definition of class. So complete set of elements which are conjugate to one another. So C3 and C32 form a class, and sigma V prime, double prime, triple prime form another class. So whatever you take that sigma V plane, multiply with any of the symmetry elements present in C3V group, you will always end up with sigma V or sigma planes. Similarly, if you take C3, you will end up with same rotational axis of symmetry only. You can check it. I think we have done it for C3 and sigma V prime. So these two we have done it, right? As a homework or as a practice, you try it for C3 2 and sigma V triple prime. Okay, so you take that and then operate all the elements and find the solution. Now what you're going to get it. Okay, so you get it. Confirm yourself. So any questions so far?
Sir, could you please repeat class?
Okay, so class I have to repeat. Say in C3V you have how many? 6 elements are there, right? C3V has E, C2, C3, C32, sigma V prime, sigma V double prime, sigma V triple prime. Okay, so class means so conjugate when we'll say if you perform this operation, it's a common general notation, B equal to X inverse A and X. So I think you might have studied this in +1 or +2 itself, similarity transformation in mathematics course. Same thing we are applying here. So you take, these are the symmetry operations. A is one symmetry operation, B is another symmetry operation. And if you multiply with A with another symmetry operation and its own inverse. Okay, so if you do that, you will end up with another symmetry element. So this is what we are trying. If you do, if this relation is valid, then we say B is a similar transformation of, no, B is A and B are complex conjugate, and we say B is a similar transformation of A with respect to X. Okay, so these are some definitions. A and B are conjugates, I mean conjugate elements, and B is said to be complex. I mean B is said to be the similar transformation of A with respect to X. So this is in general terms, but for example, I have worked out here. So you take sigma B plane from this one of the set, and then operate with any of the element, either E, C3, C32, sigma B prime, sigma B double prime, sigma B triple prime. And as you know, the sigma B, in the left hand side, you can see all inverse are there. It's corresponding inverse. Sigma B prime means it's sigma B minus 1. Sigma B double prime means sigma B double prime minus 1. So it's inverse of that. Here again, there's an inverse. So we are doing this operation. Either you can multiply with the matrix, which we have just in the beginning of the class, we don't know. You take the matrix multiplication and get the solution. If not, you use the multiplication table, which you wrote a couple of days back. So any of the method you can follow, but you can just have to operate from left to right. Sorry, right to left. Okay, from right side you have to come to left side. So that's what I was doing. If you perform these operations, you can see we started with sigma B prime. It will always end up with sigma planes only, not rotation. This forms a class. Similarly, you can try the sigma B double prime or sigma B triple prime. The center you can try and find out. You will find out the same thing. So sigma plane is one class, and rotation is another class. Similarly, instead of sigma B plane, if you use C3 or C32, you will end up with C3 or C32 in the right hand side. So that forms another class. So that's what it is. So we saw three definitions. One is similarity transformation, complex element. I mean the conjugate element. Third is class. So those complex set of elements which are conjugate to each other. Okay, it's called as a class. Now we'll see the properties of class if you have time. Okay. So this is kind of followable. I mean, you can follow it.
Yes, sir.
Yeah. So yeah, these are all new terms. It just, yeah, we'll introduce these things. We're helpful in finding out reducible and irreducible representation. That's why we're just seeing it. So you just go back and then read the books or work it out. Just as you simply, you try with this one. Find similar transformation of C32 with respect to what do you want to find out with respect to? No, that's where it comes from. That's my transformation of with respect to you can any plane you can say. So sigma V triple prime. To find out this one, this is first question. Second is so just to prove it. So first question is you have to find a similar transformation from C32 with respect to sigma V triple prime. That is, I think you can simply do it. I think, right? So simply C32 sigma V triple prime, sigma V triple prime inverse. This you have to find out what is the solution. Then you can get the answer. So the second problem is show that the three reflection planes in ammonia molecule form a class. So you have to take sigma v prime, double prime, triple prime, operate with every other element, and find out what is the product. So it says prove it. So just it says it's form a class. So you have to find out. You have to prove it that all are getting resulting in sigma v planes only, not rotational axis. So you practice this, then this concept becomes clear. Okay. For multiplying it, you have to multiply it. This thing either you can use the multiplying table which we computed recently, maybe 2-3 days back, or today we wrote a matrix, 3x3 matrix. Use that matrix to evaluate the these product. So okay, then you will find a solution. Okay, I'll leave this one now. Next class we'll study the properties of class, and then we introduce what is called as special.
Hello, sir.
Yeah.
Sir, you said na ki V is similarity transformation of A with respect to X. Sir, what it does mean, sir?
So that's the terminology used. So here also you can say if you find out what here. So C3, it could be answer could be here. I can guess it could be C3 or C3 2 only. So we say C3 is a similar transformation of C3 2 with respect to sigma v triple prime. I mean, this is the terminology used. Whatever you perform, then you will end up with a class. It doesn't. This is the way to find out the conjugate elements. This is the method used to find out the conjugate elements. So C3 and C32 form a conjugate element, and plane sigma v prime or sigma v double prime form another conjugate element, or sigma v prime or sigma v triple prime form a conjugate element. So to form a class, so this definition is used. The similar transformation methodology is used in mathematics. Same is applied in symmetry operations. Okay, just to know, to find out a class in a given group. Okay, so say all the elements are not similar, so you have to separate it out. We call it in terms of a class. Okay, for that we use this methodology. The similar transformation methodology is being used. Okay, so I think partially answered, I guess. You work it
Sir,
out.
what is the need of the class?
Okay, so what is the need of the class? So let me, because we are stopping the class in the middle, right? That's the reason. I mean, that's stopping the discussion in the middle. So if you have a matrix, I just write a big matrix, 6x6 matrix, then I'll take 2 minutes, not more than that, okay? So by say if you have a 6-atom system, and I'm writing a matrix representation of that system by this matrix, say 6x6 matrix I'm writing, and you are getting something like this. And a lot of zeros are here, and a lot of zeros are here, whereas the elements are present only in these places. So instead of what I do is instead of multiplying 6x6 matrix, say I want to multiply with another matrix. 4, 1, 1, 2, 3, 4, 2, 3, 0, 0, 0, 0, 0, 0, say again 1, 0, 0, 0. I can have matrix 0, 1, 2. Say I have two matrix by various operation. I just got the matrix. I want to multiply it. Instead of multiplying 6 by 6 matrix, what I do is I multiply only the corresponding matrix elements. Say I just transform this matrix in certain form and make it all diagonal. So you can see this part is 2 by 2 matrix, and here 2 by 2 matrix. So I just multiply only these 2 by 2 and 2 by 2, get the solution. And here it is just 1 by 1, this is 1 by 1. So I multiply only with this one and this and get the solution. Here 3 by 3 into 3 by 3 matrix. So taking the product 6 by 6 is very difficult. So we use certain techniques to bring down to diagonal matrix. So these are the results of diagonal matrix. So you can see only elements are present only through the almost in the diagonal shape only. You will find a lot of zeros here. So, and then multiplication becomes easier. So we just multiply with 1, 0, 1, 2, and 4, 1, 2, 3. That is 1. You get the solution. Next is 3 into 1. That is the next solution. Third one is 3 by 3 matrix. You will get 1, 3, 2, 1, 2, 2, 4, 0, 1, and then 0, 1, 2, 3, 0, 2, 2, 1, 1. Okay, so 6 by 6 matrix has been converted into 2 by 2 matrix, 1 by 1, and 3 by 3 matrix. So entire group, if you consider this as an entire group, we have split into 3 classes. So this is one class. 1, 0, 1, 2 is one class, which is 2 by 2 matrix. This is another class. This is another class. Okay, so yeah. Common matrix has been converted into special matrix in the form of only importance is given only in the diagonal elements. There are a lot of off-diagonal elements which became 0. So in class also we are doing the same thing. From set of elements we are separating it out into a smaller set, and we call that as a class, so that the operation becomes simpler. And we will try even whether this 2 by 2 matrix also can be converted into a diagonal matrix. Say you are just getting 1, 0, 0, 1. So can we do that? So we try to do that. So that process is called as going from reducible representation to irreducible representation. So we bring down to the matrix size to the 1 by 1 matrix. We'll try our best to bring it down to 1 by 1 matrix until you cannot do further. So if you are reaching 1 by 1 matrix, we call that as a one-dimensional representation. If you are reaching to 2 by 2 matrix, it's called as two-dimensional representation. And 3 by 3 matrix means it's three-dimensional representation. So we bring down to at least to 3 dimension. So that's what we try to do. And this process is called as class, separating into a common matrix into a smaller set is called as a class. For that, we use the similarity transformation method, which is quite common which is quite routinely used by mathematicians. Okay, so it's an application we are about to reach, but yes, yeah. So what is the need? We split into the full group elements. We split into different classes, just to make our life easier. Okay. I hope I gave the answer. Okay, shall I stop it here? Is there any other questions? Let me see in any chat box. No, I don't find any question. Okay then, so I'll share the video, and then yeah, anyway, if I scan it, I can scan the notes also. You go through it. Okay, just go back and listen, or just read your notes and try to work out which I gave you, two assignment problem, so that the concept becomes clear. Okay, we'll see slowly what is the application of doing all these things. We'll write a capture table. It could be one-dimensional type, or two-dimensional type, or three-dimensional type. For example, in your, say, it's very well-known examples are there in complexes, in metal metal ligand complexes, octahedral you can say. There you write the d orbitals, the 5 d orbitals. You split into two types, right? So d orbital, there are 5 types, right? You split into what? P2G and EG, no? How do you write EG, right? You split it, right? So what is T and what is E here? So our aim is to go to this way. T stands for 3 dimension. Its representation is 3 dimension, then you have 3 orbitals, and here it will be 2 dimension. So the big 5 matrix, 5 level matrix, you can say D as 5. That has been brought down to, you have split into two states. One is 3 dimension, and other is 2 dimension. So in complexes we have studied, but we'll connect to that, and the group theory is very helpful in doing that. So we split the d orbitals, all the d orbitals, d x y, d z square, d y z, d zx, and then d x square minus y square. 5 orbitals split into T2G and EG, right? So what we have seen is, to consider this as one group, we're splitting that into different classes. So this is of 3 dimension, this is of 2 dimension. So that's what we do it. So in matrix form we have seen, but let's see it in orbitals. And slowly we'll do that. Okay. So I will connect to this in the end. So I'll stop the recording.